So the premise is the liquid-liquid phase separation, and we talked about a typical phase diagram like this. This is volume fraction of polymer of any kind, and this is say temperature, and then we got a curve like this. That's the coexistence curve, and there is some critical temperature, and then underneath this is spinodal curve. And outside this, everything is homogeneous, completely miscible. And that's what we did, right? And we said the premise of these biomolecular condensates, which are constituting these liquids formed in liquid-liquid phase separation, comes from some partition, some like this one. All right. I just in the very first lecture, I told you that this is something like sum over all possible conformations and many chains. So I'll put like this, right? And then something like this. I wrote down something like and then I wrote down something like sequence and various potential interactions between 2 points on the polymer chain. So in forming this phase transition phases, and the constituent molecules are like this, are peppered with charges.
You may not have written this expression in this course. Yeah. I think it was
I thought I did in the very first lecture, something like this.
Yeah, you did.
We'll come back to that. Don't worry.
Yeah, it's fine. It's fine.
Yeah, we'll come back to that. But this is the premise. Maybe I didn't do this, but it's okay. I'll explain to you now. There are some neutral groups, positive charged groups, negatively charged groups. So there is a sequence in which these monomers are tethered together. That sequence is given by here, and V is interaction between any 2 monomers. The monomers are making the polymer chain, right? And there are many such chains. I'll explain to you in about a few minutes how to deal with this one. So this sum and integral means that there are many components, there are small ions of water, we have to integrate over all those degrees of freedom to get the free energy of the whole system, V minus free energy by KBT. This is what one should do, right? In the last 2 lectures, what we did was we created a mean field theory, the Flory-Huggins theory. That's what we did. And the Flory-Huggins theory, we simply assumed the repeat units are more like without any rich details except nearest neighbor interaction energy, short range nearest neighbor interaction energy, and then we defined this chi parameter to account for energetics of different kinds of pairing. That's what it is. And then we calculated the entropy of mixing in the mean field way, and then we calculated the free energy. Right? And then once you calculate the free energy, you can calculate the phase diagram, which we did in the last lecture. How to compose phase diagram once you have the free energy. Right? This, for example, this red curve corresponds to the second derivative of free energy with respect to this volume fraction being 0, and the yellow curve corresponds to 2 daughter phases coexisting in such a way the chemical potential of each component is the same in the 2 daughter phases. If there are 10 components, 10 different kinds of molecules, for each one of them chemical potential should be the same. But the chemical potential of component 1 will be different from the chemical potential of component 2. But for a particular component in multiple phases which are coexisting, chemical potential should be the same. If it's not the same, then system is not in equilibrium. Then they will evolve to make sure the chemical potential is the same. Okay, that's basically the summary of what we did.
Can you explain this expression like one more time?
I'm going to do that. That mathematical expression?
Yeah. What is RS?
Yeah, we will do that. We will do that.
So just curious, is this Hamiltonian called the Edwards Hamiltonian?
Just wait. Yeah.
Okay.
Just wait. Yeah.
So I have one question. So in general, if I have the free energy, that should contain all the information about this. I mean, if I have a partition function, that should contain all the information on the system. And if I get the free energy from that and minimize the free energy, shouldn't that automatically lead to chemical potential? I mean, I think you made this point. I want to understand this.
No, indeed, right. So the once you have the way the roadmap is this: you start with a Hamiltonian, which I'll explain to you. This is a Hamiltonian with some names, right? There's a Hamiltonian. You describe the Hamiltonian that is appropriate for the particular system that you are interested in. Then you do statistical mechanics to integrate over all degrees of freedom to get the free energy, right? The free energy is a macroscopic quantity that's valid for the whole system. When you say whole system, I am talking about length scales which are infinitely large. Therefore, I do not have any information about local details anymore because I am integrating them out, right. So, the free energy is corresponding to a very large wavelength system, very large length scales. It's okay, large length scale systems. Then given that, you calculate the chemical potential. That chemical potential would be again a large scale quantity, and then per molecule in that system, what is the free energy per molecule? That is the way you get it. And then you go through the method of determining the phase diagram. All right. So, before I go further, I like to take a brief moment to tell you about the internal structure, right, which we did not talk about it. We just said, oh, we just throw them randomly and then calculate the free energy. But I think for practical purposes, I like to know, for example, as you can tell, as I kind of alluded to in the last lecture, here is one polymer chain, your favorite polymer. In dilute solutions, I cannot imagine this chain, the monomers of this chain are distributed homogeneously in the whole box. Of course not, because this monomer knows that it is connected to this single molecule. It knows that this is his or her sister, right? Same, several monomers are tethered together, so they are topologically correlated. Right? That correlation would be missing in the Flory-Higgins theory when we spread them randomly, right? Here to missing. So, let me take a brief moment to talk about the structure of a coil like this, one polymer chain. Okay? And then we will generalize that to go to higher concentrations. So,
in the Flory-Higgins theory is valid for the concentrated solutions. So if we want to try out the dilute solution, should we add some terms in the Flory-Higgins theory, or we should go to some another theory?
We will have to do it.
In the Flory-Higgins itself, we can add, or
not that simply. Yeah, we will see. We'll see. That is our goal. So, that is number one. Second thing I want to tell you about is this. When you take about today, that is our outline. The biomolecular condensates, what is the typical temperature that these condensates form? Basically physiological temperature. Yeah, 37 degrees Celsius, around that temperature range. So, therefore, in most of the biological problems, temperature is not the key variable, right. When our body would not function when the temperature is 10 degrees Kelvin, right, or 400 degrees Kelvin. So, the key variable is salt concentration. That is the key variable, right. If you take more salt, less salt, immediately you know what is happening, right. So, salt is the variable. So, in this axis, I would say there is one more quantity instead of T. I will probably talk about what the consequence of salt concentration is. Okay. And as you can intuitively tell, salt concentration is pertinent, is important only if there are electrical charges, right, in the system. Only when there are charges in the system, then salt can play a role. Then you can screen it, or no, they do not screen it, what have you, right. So, that means there is also charge density, that is another variable. Let me write charge density as a Q along the polymer chain, right. And how do you tune Mother Nature? How does she tune the charge density? The way she does is through pH. right? I'm sure from personal experiences, you know pH plays an important role. You know that how things happen. What is pH? pH is negative logarithm of concentration of protons. So in the system, acidity, not acidity, all these things are extremely important. More than temperature. We use the temperature to illustrate the concept because it's a very convenient variable to do physics, but in biophysics, I have to worry about those things. Okay. So there are two things we are going to do. One is to worry about electrostatics on polymeric systems, right? And number two is dense phase. How do you go from here to there? Structure. How do you go from here to semi-dilute? So you interpenetrating chains. And then the question then is, would the structure that I have here would change drastically in a collected system, collection of strings? Would there be a new structure, and how does it happen, and things like that. These things will not be observed in a Flory-Huggins theory. The Flory-Huggins theory does not have any capability to talk about a structural evolution, right? But that's important. That's what we want to do, because if you want to have these molecular condensates, and then when you want to have these molecules recognize each other, they have to recognize, they may have to pair, unpair, and the structure is important, right? If you have only one spherical particle, another spherical particle, if you take them, that's kind of dull. They come and go like this, go out. That's not important in biological systems. But if you have stringy things and they can interpenetrate, there's a lot of structure, they can evolve in a very nice way, and we should develop capability to describe that kind of interactions. Okay, so that's the outline of what we are going to do today. I hope we can finish them. Otherwise, you have to hang around, because I like to finish this today, because on Wednesday I like to talk about kinetics of structural evolution. I want to talk about structural evolution today in equilibrium, and then let's see how the structural evolution would come about as a function of time. Oh, that's on Wednesday. Okay, let me take the simplistic case. The simplistic case is a chain of a random walk. Right? If I have a random walk in 3 dimensions, like this, keep going, and we can imagine this to be a chain. I start somewhere here, right? A continuous chain like this, random walking chain. The random walking chain is written, right? The conformation of a random walking chain, a conformation of a chain without any interaction that I am talking about, with any exclusive volume interactions, right? That is written by this term. Okay. This basically says dr, r is, suppose I write a chain like this, this is the location of one of the monomers, S monomer, and S monomer, there are n monomers here, S starts from 0 and then ends with n along the contours. 0, you walk along, so I go to 112 for example, and then this is 213, and then go on and on, 512, tell me, 1000. It's a label. Little s is a label for the index of the monomers along the polymer chain. So locally, right, when I take the tangent of this, right, that would be my dr by ds. R is a 3-dimensional position, s is an arc length variable, so dr by ds is tangent. Square of the tangent gives me the connectivity of this polymer chain. Only chain connectivity, nothing else. Okay, so that's the starting point, right? That's what that means. What the way you imagine this is, you could imagine that this is the mapping of a trajectory of a random walking ant, random walking electron, random walking anything. Right? Trajectory as a function of time. So as the time is clicking, I make one step, right, of length L. Let me write that is length L. This L, and then I make next step without any memory of what I did in the past, and then go to new position, make another next step, another step, complete random walk. If you do this, that is described by this one. And as you know from your elementary statistical mechanics, the probability of reaching the end of the chain all right. Let us assume the other end is here, that is my R capital N, this is my initial position, 0 somewhere here. The probability of getting R, one end is at R, other end is 0, that can be written from random walking statistics, 3 R square over 2 N L square. N is number of steps you make, and then there is a prefactor 3 over 2 pi N L square 3 by 2. That is a prefactor, that is not important, but that is it's a Gaussian, right, it is a random walk, Brownian motion if you like, in terms of time, but now time is N, arc length, the time variable is arc length variable, so that is the distribution function for end to end distance.
It is only true when there is no interaction.
Correct.
Also, should the step length be constant or L can vary?
L can be fluctuating in a normal way, when normally distributed, you get the same answer, or it could be fixed number, as long as capital N, number of steps is long enough, you will get this.
No, in the free energy expression, like that is valid for this fixed L or like any fluctuation?
It's valid. That's valid for any fixed L or fluctuating L. Fluctuating L.
Normally distributed.
Normally distributed. Yeah. It's okay. So I'm not talking about any of these things yet. I'm just talking about only this term, right? Okay. Okay. Yeah. All right. So the for a random walk, I can calculate. See the way I drew this cartoon, right? Not deliberately, but that's the way it turned out. There is a typical size of this coil, right? Let me write that typical size to be radius of gyration RG. So it's almost like a ball of wool, right? It's a fractal object. It is not a rigid potato or tomato, right? It's really a porous material. It's completely highly fluctuating. It's not rigid, but on an average sense, we can define RG. This RG turns out to be for this model is N L square divided by 6 in 3 dimensions.
Are you considering globular structure?
No.
Also, can you explain again why del R by del S square we have to have in the free energy? Like
because it's a tangent, right? It's changing the direction, right?
Yeah.
Right. So yeah, the other way to look at it is every step. So you know, we should have all those lectures in one place, right?
Exactly. I know it.
Right. Okay. So okay, let me take this step, right? Okay, this is my j plus 1, okay, j plus 2, okay, or s plus 1, s plus 2, right. So this bond is vibrating. You said that, right? This bond vector is a position of j plus 1 minus rj, okay, and that has a dimension of length, and the bond length is L. Okay. Then what you do is, okay, so but it's a harmonic oscillator, right? Let's assume it's a harmonic oscillator, and then harmonic oscillator will go with the displacement square. Energy will go like displacement square, right? So I could just to make life easy, I could write like this, and that is that term. Okay. So basically, it says that these bonds are connected together. Similarly, I go to the next step, and that's why I have the integral over S here. Okay, good. Okay, so the other property is the following. See, it's very difficult to measure. How do you measure RG? Right? This is my radius gyration. Is this exact theory tells me this answer, but how do I measure the size? How would you measure the size? It's a 3-dimensional object hanging around in a solution. How would you do it? Scattering. You would do scattering. Yeah, this is, incident beam comes, gets out, you measure this, right? Okay, so what you measure there is the following: the scattering intensity, right, which is proportional to, let me write structure factor S of k. And k is a scattering wave vector, right? There is an incident beam with a wavelength lambda. Here is my sample, and here is this theta the angle at which the detector is subtended with respect to the incident beam, and this k is equal to 4 pi over lambda sine theta over 2. I think I mentioned the last lecture. I think you change the angle depending upon the contrast, you know the wavelength, right. So, for this model, suppose that the incident beam comes in here into the coil, because coil is big enough, right. It goes inside here and gets scattered by the various units, and then the light is coming out. If we do this, this is equal to, after normalization, summation over I, summation over j, e to the I k dot r I minus r j, and of course average it out. I is ith monomer here is somewhere is ith monomer, here is somewhere jth monomer. So, the constructive superposition of scattered wave is given by this formula, e to the I k dot r I is one wave coming out, I k dot r j is coming out from the another beat, and the negative sign because of the constructive interference, and then sum over both I and j, and then normalize this. So, the total intensity is proportional to n. This will give me a factor of capital N, this will give me a factor of capital N squared divided by n, that will give me n. That is the total intensity should be proportional number of units which are scattering. Now, a nice thing about Brownian motion is we can do everything with paper and pencil or in your head. You do not even need a paper and pencil, you know. And anybody who is interested in stat mech, theoretical physics, experimental physics should know a great deal about Gaussian distribution. How to take first moment, how to do the integral, how to take the derivative, what is the width of Gaussian distribution, that is given. Everybody should know that, right. And since this is a moment using Gauss in this distribution function, this turns out to be equal to 1 over n summation over I, summation over j, e to the minus k square L square I minus j over 6. This is something that I did in the another class somewhere else. Okay. Because you average it out, that is, if you average it out with the Gaussian distribution function, completion of squares, you do the Gaussian integral, you get this answer. In the other class, Sandeep, I had capital N instead of I minus j, but I minus j is now I. Yeah. So, let us do this summation. Okay. This was done by Debye, Peter Debye. Okay. And no escape from Debye's work if you want to do polymer science or biophysics. You probably do not know this, because you are thinking about Debye's specific heat correction for Einstein's calculation, and on and on and on. But he was a great contributor to the physics of polymers and biopolymers. All right. When you do this, what you get is the following: S of k turns out to be equal to 2n k to the 4 r g to the 4 e to the minus k square r g square minus 1 plus k square r g square. There was some input from some of my friends here. Maybe I should assign some homework problems, right, for both of you or all of you, right. You can do this as an example. How do you get this from here? Because this is a very famous formula and it is loaded with information. Right. And this is, in fact, makes the principle of experimentation. The way biopolymers or synthetic polymers are characterized is using that expression. That is the theory, and this is the experiment. Even Debye was also a great experimentalist, right. So, he would do this experiment and he would do this theory, he will match these two and then determine everything. He will determine the molar mass of the polymer, how big the number of monomers. He will also figure out Rg, because N appears here, Rg appears here.
So, he did it in the context of polymers?
Yeah. Yeah.
So, was it like structure factor was initially in the context of polymer discovered?
Well, in liquids also, right?
Yeah, I mean, because you can study various
things.
Oh,
yeah.
I'm wondering, so if this is the first.
Polymer physics is a very mature field, right? Polymer physics is a very mature field, and it's extremely rich and complicated. It takes a while to learn because it involves a lot of things. It involves hydrodynamics, physical mechanics, quantum, of course mathematical physics, all the techniques that we use. It's really very, and you heard some field theoretic methods. It's really very beautiful field, and unfortunately it is not taught in undergraduate programs. Therefore, most of the people do not know. Even in IMSc, I'm not sure how many entering students know about the beauty of this field, right? Okay, anyways, okay, what's going on here is this. Here, you can expand this. K times Rg is much less than 1. You expand this, you will get something like this: 1 minus K square Rg square divided by 3 plus etc. That's what you'll have for that limit. So what you do is you go back to this experimental setup, take theta to be small. When theta is small, sin theta is small, therefore k is small. If k is small, then this expression becomes like this, and you measure as a function of different k, and you get Rg, and then when you extrapolate for small values of k, you get n. So, single experiment you can get n and Rg, molar mass of the polymer, and also radius gyration. Okay. But now, instead of looking at
So this is the linear approximation?
not yet.
Not yet, right?
Not yet. This is the device Zim. This is Zim. Yeah. This is Zim. But if you take an exponential of intensity, then that will be linear.
Okay.
Because then you make an approximation exponential of 1 minus right is e to the minus yeah. But let's sit with this exact result. The other limit, this is important. The other limit is k Rg is larger than 1. Okay. So what does that mean? I mean, this is a general question for people, right? If I have a polymer coil like this, I'm going to write it and erase it because I need some space, like this. All right. This is my Rg. Okay. I'm looking at k times Rg larger than 1. Right. K is typically like k is like 1 over length. When k is large, right, the observation length is small. That's the meaning of k being large. When the observation length is small, what I'm doing is, this is my observation length scale. Typical length scale is into the polymer chain, dimension of polymer chain. So there's an opportunity to know the correlation, how the monomer density is correlated inside the coil, if I were to design my experiment so that I go into that limit, k Rg is greater than 1 limit. Let's do that. If you do this, the answer turns out to be, so this is very large number, this is e to the minus larger number goes to 0, this is large compared to this one, then this dominates, and then I have 1 over k to the 4, here I have k square, what I get is a k square, okay, and then I have 2n Rg square, and I wrote down Rg, this is Rg square, excuse me, Rg square goes like nl square over 6, then I get 1 factor n goes away, L square 12. That's what I get. Okay. The important thing is, this quantity goes like in this limit, it goes like 1 over k power some number df. This df is called a fractal dimension. Okay. With df is equal to 1 over nu, where nu is defined to be, where nu is Rg. Rg is proportional n to the nu. The relation between the size, radius of gyration of the polymer with the number of monomers in the system in that polymer, that exponent Rg going to n per nu, right, and nu is equal to half for this system. For a Gaussian chains, nu is equal to half, and therefore I have df to be 2. 1 over half is a 2, 1 over k square. I can do this calculation generally for any other system, even with the interactions. Then this formula is true, 1 over k to the df, and if you measure this, you can immediately get nu. If you measure this, you can get nu. That's another quick and dirty way, an economical way to determine the size of the polymer as a function of molecular weight. But the important thing is, if I plot S of k, all right, that will depend upon k like a inverse square only due to random walk. Okay. This is a very general result. Instead of talking about polymers, if you talk about the dynamics of a particle, random walking particle, you have lots of trajectories in the simulations, and if you catalog them and look at spectrum, right, spectrum of that will behave 1 over k square. It is a theorem. Okay. Okay, so now we know something about the structure. So in a Flory-Hagen theory, you have none of these things, right? There is no correlation at all. Okay. Any other comments? Okay. Let me give you one more example. Since we are talking about a single chain here, suppose I do the following experiment. Right. See, as a theorist, we should think like an experimentalist. Right. That is what we should do. What would I want to do in an experiment? Then you compose a theory for this. Not the other way around. Okay. Right. So always we think it as a what should we do? Suppose I go to this problem and I hold one end here, and then I have a tweezer. And my experimental colleagues tell me what kind of tweezer I should use, right? Because then I ask them, hey, what do I want to put on the other end? I want to do this experiment, and I hold the other end and I pull it. All right, and what will happen? Is it easy to pull it or harder to pull it? That's the question, right? And in order to do that, the answer is already, oh, if I want to know this, I already know this, because I go to this term, the free energy of a single chain with the end-to-end distance r. I go in here, free energy with the end-to-end distance r by kBt. This is, I'm taking a chain with one end here, other end in here. This is my r, capital R, end-to-end distance, and there are n monomers. What is the force that is holding it together? Right? In order to get that, let me get the free energy, and then when I take the derivative of the free energy with respect to r, I'll get the force. Gradient of free energy will give me a force with a negative sign, right? So this is the free energy. How is that going to be? That should be obvious by even just staring at this, right? You don't have to do too fancy calculations. How do you do this? Here is a one dimension r square. Here is one dimension of a length, monomer length, number of monomers, s square, and then here is s, right? So when you do, right, and then there is a length square. Okay, excuse me, wait a minute. There is no dimension for s because it is only a number. So what I get is a r square, right? This one give me a factor of n. Here I have factors of n square. So I'll have r square by n, a little l square. So what I will write is r square n l square, and then I have 3 by 2. That's what I would do. Gaussian chain. Other way of doing that is I go and look at this formula. This is the probability. A logarithm of probability within upper Boltzmann constant gives me entropy, minus temperature times entropy gives me free energy. So that minus sign will kill that minus sign, and I'm dividing by kBt minus kBt 3 by 2 r square L square, right? You could do the hard way, do the calculation and get the free energy, or inspect it and then boldly write down the free energy expression. Why not? Okay. But the important thing is, if I stretch the polymer chain with a tweezer, the coil gets unraveled. It is not a haphazard object anymore. The coil gets unraveled. That means that the degree of randomness goes down. That means entropy goes down. Therefore, free energy goes up. So I pay a penalty. I have to do a work to stretch the chain. but how easy is it to stretch? This is more like your harmonic oscillator, or is more like a Hookean spring, if you like. How hard is it to stretch? That is dictated by this number 1 over n. The force constant is 1 over n. And what is the n? N is 1000, 200. So 1 over n is very small. So this polymer chain is a soft matter. It's very soft, right? The force constant is so tiny. Mother Nature plays magic. The chromosome can expand easily. You can compress it. You need only piconewtons, very small amount of forces, to do all this dance, macromolecular dance. It's not like a chalk piece like this. If I want to stretch it, no way. I cannot stretch it. Or sugar cane, no way, right? So that's already a secret, right? There are many reasons why evolution chose polymers, right? There are many, right? Okay, so good. And that's about a Gaussian chain. This is called a Gaussian chain because this distribution function is Gaussian, and therefore there is no interactions whatsoever. That's what that is. Now what I like to do is I like to slowly creep into putting interactions. Okay, let's do that. Any questions before I go? Yeah.
I had just one question. So this nu you talked about. So we call it the Fleury's exponent. So historically, how that name came about? I was just wondering.
Right, right. As I was telling you in the another lecture, there is a mapping between polymer problem and the critical phenomena and also field theory.
Right.
There, the correlation length diverged with temperature like nu minus nu 1 over t minus T3 nu, right? The correlation was a divergent.
Right.
So here the radius gyration is the correlation length for this polymer chain to be tied together. Therefore, this is also diverging with n. How does it diverge? It diverges with a n power nu. That's the reason. But if you take earlier textbooks in polymers, they don't use nu.
I see. Okay.
They will put some other number,
Okay.
alpha or something like
I
this.
see.
Yeah.
I see. Okay.
Yeah. But anyway, it's only a symbol.
Symbol.
Yeah. Yeah. Please.
We are using n tends to very large limit and getting the fractal dimension df. So if I am working on, let's say, very short peptide, so what should I do to incorporate the length?
Well, all these things are valid only if the length is large enough, right? Length is large enough. If it's not too long, you cannot use this statistics, right? And I give you a homework assignment. Please go and look at the book by Yamakawa. So, and this book has an answer to your question. Okay, Hiromi Yamakawa. And it was written in 1972, and the title is Modern Theory of Polymer Solutions. That's the title. In those days, that was modern theory, right? Because I don't want to digress away from specific questions in here, because we want to look at the general problems today. Okay, so let's begin to talk about this one. I already told you in the last lecture here. We draw a lattice, right? And then we define chi parameter to be z over, what is this, kt, epsilon 1 2 minus half epsilon 1 1 plus epsilon 2 2. Remember that? No. Type 1 interacted in type 1, type 2 interacted in type 2, type 1 interacted in type 2. That's what we did, right? Now let's not worry about the lattice, but instead we will think about a polymer like this. Okay, if you have a polymer like this, right? So let me take a chain like that, and let me look at the interaction between this and this. Okay, let me say this distance is r, this is ith monomer, and this is jth monomer. Let's say, or its vectorial distance r. So, what is the energy, before I go in there, what is the energy as a function of R in kBt units as a function of R? How is that going to look like? Right? It's simple. Yes, this interacts with this one, and there are also solvent molecules. Solvent molecules, they interact, and the solvent molecule and this monomer, they interact, and monomer interact. So, again, just like that one, we have three interactions: polymer, solvent polymer, solvent to solvent. We do not know, our technology, I know some of you are doing lots of simulations, but with a great respect to those who do simulations, we still do not know good potentials, right. So, our answer, I can create any answer I want depending upon the choice of the potential, right. But nevertheless, generically speaking, it is going to look like this, right. But at short distances, it will be repulsive. At large distance, there will be nothing, and in the middle, there will be attractive, van der Waals, what have you. I have not put any charges here, just simply neutral cases. So, what I like to do is, since I do not know ab initio values of the potentials between various atoms in condensed phase, we are not talking about space, we are not talking about vacuum, right. In condensed phase, we do not know what the potentials are. Therefore, I am going to surrender to say there is going to be a parameter, I am going to parameterize them, and then I will make measurements to calibrate my parameters and then match them. That is the strategy I want to do.
So, is it possible, like using quantum chemistry or something?
It should be possible. I hope your computers will be fast enough to really address that problem. This is one of the challenges for future generation. I'm not going to do that. It's a really very important one. And we are talking about density functional theory, quantum, things like that. That's what we need to do. But not in space. All the DFT that we do is in vacuum today. So that is not enough. Okay? Polarizability is a huge challenge that all of us should be thinking about seriously. Good. It's an ideal project for IMSC. Sandeep, ideal problem for IMSC. I pick on him. He's my host, primary host. Yeah. So he needs to be treated well. You too, Devayan. Yeah. Okay, right. Okay, all right. Let's go. Okay, so what is in statistical mechanics? What is the key quantity that tells me that something is going to be close to a monomer, right? That's a radial distribution function, right? So I'm going to construct a 1 minus e to the minus kBt. This is u r, right? And I'm going to integrate it over dr. This is a second virial coefficient, right? This is how pairwise, effectively how two monomers come together, and this is also right. Okay. Okay. And I'm going to parameterize this. I'm going to write this to be equal to V, right? Look at this. This is 1. There is no dimension, right? dr is 3 dimensions, right? 3 dimensional volume. So let me write L cubed, monomer length. Little l is a monomer length, L cubed, and then this is the parameter V. This V is called excluded volume parameter. It is not an excluded volume. Many people, even books, say erroneously, it is not an excluded volume, it is an excluded volume parameter. This parameter is a representation of all the chemical details. All the rich chemical details is a representation of my ignorance about these interactions, the potentials.
And usually, is it that that's an effective parameter that you determine by comparing to experiments?
Yeah, we'll see. The question is, we'll come back to this question. Maybe somebody else can answer this question. Is there any volunteer there? Otherwise, okay, somebody is going to answer this question. Okay, so
I don't understand
how this parameter would capture the potential, like how this parameter will capture the potential.
We'll do it. We will do it. We'll do it in a minute. Now, without any, instead of surprising you, I tell you this is also equal to 1 minus 2 chi L cubed. The same chi we talked about. Okay. We talked about two body interactions there. It's the same as it's related to this second virial coefficient. Now, Sandeep, you know the answer. How do I get V? We talked about measuring chi parameter,
Yes.
right? Neutron scattering.
Okay. That's how you would.
That's the way we come back here. Yeah. But I'm coming through the back door. I introduced the lattice theory. I did the now I'm coming back to structure, right? And I'm really trying to write a Hamiltonian because I know how to get there. So I'm working backwards to write a Hamiltonian. I'm just sharing my experience, how I think. Right? Okay, so let's see how does it look like? Why does it? This is a beautiful question we had. How does V reflect that potential? Let's think about that. Right? We always think about it, right? Don't rush to computers. Okay, let me plot V, that parameter, right, as a function of say temperature. Okay, how would it look like? This is my potential. So if the temperature is very high, I have 1 over temperature. So this is small. If this is small, e to the minus something is right, nothing. Right. So what will happen is this is going to dominate. Okay. Or the other way to look at it is, if the temperature is very high, only the repulsive potential is going to be felt. Right, because it's like a gas instead of a liquid, right? When only the repulsive potential is more important, then that means U is a largely positive. Although that's a shape, U is largely positive. So e to the minus U large number, that's going to be zilch, goes away. So this is going to be positive number. Okay, what is the number? Positive what? Points at 10, 0.1, 100, depends on the chemistry, but it's going to be somewhere there. I did not put the scale here, it's going to be positive. Now let's look at the other way around. When the temperature is low, what will happen? When the temperature is low, then going back to your comment, the attractive potential is going to be felt. At low temperature, then they are going to come close, they are going to condense, right? This is going to be felt. That is negative, right? U is negative there. When the U is negative, this is negative, negative, positive, e to the positive number is large. The negative is this side, second term is going to win. Therefore, the whole integral will have a negative sign. So that means at low temperature it's going to be somewhere here. So in general, given this potential, no escape from V looking something like that. Okay. And there is a special temperature depending upon the particular chemistry of the polymer, protein, and the solvent, salt concentration, whatever you have, at which, right, V is 0. When V is 0, that means what? There is no extra volume interaction at all. And when V is 0, I would get so-called ideal condition or theta condition. Then the Gaussian chain statistics appears to be valid. Although the fractal dimension of 2 that I wrote down and Rg going like square root of n, these things have turned out to be valid, and at one special temperature, which is the so-called theta temperature. Okay, and just for the nomenclature, you will see in your when you read the review articles and papers, this condition is called a good condition because the chain is able to expand. Below theta temperature is called a poor condition, right? Somebody pointed out a globule, and that's where the polymer chain is going to be shrunk. It doesn't like the solvent, and therefore the solvent is a poor solvent for the polymer, and then it collapses state. Okay, and somehow I had to bring this up into my Hamiltonian, right. I have to write this here. How do I do this? This is what a pair of monomers interact. The way we do, right, people do is just like in liquid states and with statistical mechanics, is the following. Since this is like this integral is going to be this number. Okay. Let me assume u by kbt, this one u of r by kbt. Let me say that's equal to v delta of r, the delta function, short range interaction. It's since it's short range, let me write like this, right? And this is not quite right, as you know, because v has no dimension. This integral has a dimension of L cubed. Delta function has a dimension of what? 1 over volume. Therefore, write L cubed here. That's the volume. This 1 over volume. That's v. V is no dimension. So u r by kt. Let me write like this. The reason I do that is I take this and substitute back in here. Okay, and I do high temperature expansion. High temperature expansion means this is weak quantity, u by kt is weak quantity. I expand that. So, e to the minus that minus x is 1 minus x, 1, this is a negative sign, 1 and 1 will cancel, minus x times minus a plus x, then I will get that thing. This delta function will go here, dr delta function will make 1, I get VL cubed. This is the way we write our Hamiltonian. Right, the way.
Writing only the repulsive part. The potential.
Well, at this moment, I am looking at high temperature. I am looking at the high temperature here.
Also, but here I had one doubt. Like for low temperature, you said the potential will be negative because R will be less. But if the temperature is low enough, R could also be positive. You could feel this repulsive part if the two monomers are coming very close to each other.
They can't, because when it happens, right, you're right. What you will see is if it's attractive, it will collapse more like a black hole based upon what I have written so far. It will collapse. Maybe that's what you are allowing. At low temperature, it will condense, right? Gas becomes a liquid, right? Similarly, it will condense, right? Then you don't want to have a black hole because that's not physical. Then you have to revise the theory by allowing for 3-body interactions. Here I have written only 2-body interactions. We have to write 3-body. When many monomers are coming close and condensing, then they are only pairwise interaction is not enough. You need to worry about multiparticle interaction.
No, here this potential does not allow it to collapse like a black hole. Because
It will. If it will. If you make a u negative, well, just wait. Yeah, just wait. Yeah, it will. You just wait for a second. Yeah, we'll do that. Right. I don't want to talk about a collapse transition, but that's not what we are interested in today. But I'll make a small remark since you asked the question. Okay, so that's the potential. So therefore, what I will do here is I will write this term to be minus. Forget about the sequence for the time being. So ds 0 to n, ds prime 0 to n. This v would be v L cubed delta of rs minus rs1. Okay, this term, the interaction term with the short range interactions will look like this when v is positive. Because I am doing high temperature expansion, v is positive. I am taking v to be positive. So far. Okay. Okay. Now, what is the consequence of this? We can ask. So I have the entropic conformational entropic term and have a 2-body interaction term. And 2-body interaction term is I am taking repulsive right now, because that's the way we compose the theory. Okay. So I am going to erase this. Is it okay if I erase this? Because I need more space. Is there any space there? No, I want to work here. I am going to erase this, right? So we have the technology which if you go to the other series of lectures, you will know how to deal with this kind of stuff. This one, e to the minus 3 over 2 L square, this term minus half this term, this is called Edwards Hamiltonian. the way. This is Edwards Hamiltonian. And in IIT, we were talking about how he was a pioneer, how he created this whole field of a modern polymer theory, and that's this guy, Sir Sam Edwards, right? Okay, so I'm going to make our lives very simple. I'm not going to do too much mathematics. Just let's stare at that equation. So the free energy, right, with but in units of kT, with some size r, n to n distance r, which is proportional to radius gyration, that's equal to, I'm going to put a dot here because I'm not going to pay attention too much to in terms of prefactors, which we can work it out. This term I already told you, r square divided by n L square. I'm not writing 3 by 2, all right? R square, 1 factor of n square, 2 factors of n here, n L square. Now let's do that one. That's equal to the minus n plus, okay, V L cubed, okay, V L cubed. This is 1 over volume. Typical size is this, 1 over volume, that's going to be r cubed. Typical size is r cubed, and then there are 2 factors of n, so I have n squared. Okay. This means when I stretch the polymer chain, it's unfavorable entropically because I'm losing randomness, but from the external volume point of view, I'm releasing strain, because opening it up, the number of contacts I'm going to have is getting less, so they are going to be okay. So this favors expansion, but this does not favor expansion. What do? You optimize this. The way you optimize this is take the derivative of this with respect to r equal to 0, that's force. If you do this, again I'm forgetting about 2 r over n, and then here's the negative 3, forget about it, v n square r 4, and that's equal to 0. And therefore, when you do this, your r goes like, right, equate this v to the 1/5 n to the 3/5. People get Nobel Prizes for this kind of calculation. Flory, and this is called Flory radius, F. Flory is another Nobel Prize, right? Flory. Same Flory again series, that guy. RF goes like n to the 3/5. If it goes n to the 3/5, you know the exponent nu is 3/5. I already told you, then the structure factor S of k will go like k to the negative 5/3, right? Fractal dimension is a reciprocal of nu, I told you, as 5/3. Everything comes very nicely. Everything is experimentally validated. This is particularly true for IDPs, you will see. Right. This is particularly true. This particular result is true for IDPs.
So when are you talking about the large temperature limit? What is the
repulsion is dominant?
no? What is the limit? I mean, we are looking at the IDP at physiological temperature, 37, the body temperature. So that is the limit, the large temperature limit.
I know. This is a brilliant question, right? We should divorce away from this temperature thing, high, low, everything, because I told you in biocondensates, salt is going to play an important role. But it turns out if you do the theory properly, I'm not doing the theory properly, the key variable is V times square root of n. That would be the key variable, turns out, when you do proper theory. You can probably look at it and then write down this one. So the temperature, this V here, V is somewhere there. This V is equal to T minus the theta by theta, right? So, what is important is not the temperature is going to be very high or so, it is this number that is going to be high. The temperature could be only 39 degrees Celsius, Celsius, right, but the n could be large, and then this becomes very large. So, that is the we call this is called a fixed-point parameter. That is the dimensionless parameter that is important in these problems. Okay. So, the length of the polymer plays an important role. Right. Good question. Yeah. And we don't want to burn ourselves. When you go to high temperature, we don't want to burn ourselves, right? No, that's not possible. See, the nature evolves. It designs dimensionless variables in a proper way. Right. Okay. Good. Sorry.
If this B and root n, how is this related to temperature?
We just wrote down. This is temperature in the neighborhood of the ideal temperature. That's almost linear. So V is T minus theta. Yeah. 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 And that's why we want to be somewhere there, right? But because your square root of n comes into play, that's a dimensional variable. Okay. So we are done with this neutral case, uncharged case. Now, what I like to do is let us get into again in so temperature. Oh, before that I should make a comment. I want to talk about charges. I want to make a comment about this. Suppose I go here in this equation. Suppose V is negative. I am asking you. Suppose V is negative. When is a free energy minimum? V is negative. For what value of R? Here when V is positive, we optimized it, right? V is positive, we got this. Suppose V is negative, and when would the free energy be minimum? At what value of R free energy would be minimum?
0.33.
No, they will not get. Yeah, the equation is it will be positive, the R by n plus e to the.
No, I am talking. You look at the free energy. When is the free energy going to be minimum? Given this, when is the free energy going to be minimum? Any help from his friends? When is that free energy going to be negative? If V is negative.
If V is negative, it can go up to. So R negative. That means R negative. It's not.
No, R cannot be negative.
Yeah. So
What the physically R can only be positive. When does the minimum occur? I am asking a very simple question. When R is equal to 0. Yeah. When f is equal to minus infinity. When R is 0, this is negative sign. When R is 0, free energy goes to the minus infinity. R is 0, that is a black hole, and that is not possible. So when V turns to be negative, the 3 body interactions play a role. This theory, then you have to append in here, you have to append not only the 2 body interactions, but like interactions like that, and 4 body interactions to stabilize your globule. If you do the globulization of a polymer, you cannot stop with the 2 body interactions.
So now, can we modify our 2 body interaction in a way to capture this effect? Like rather than explicitly considering 3 body or higher order interactions, can we just modify a 2 body interaction term where I just.
Well, yeah, no, I think what you will do is instead of writing V, you write a V effective, right, which would depend upon V effective, which would be equal to V times 1 minus the density or something like this. But that is cheating, right? Because that density comes from the 3 body interactions.
So how high can you go in terms of the number of like the higher order interactions?
Oh, the answer, as soon as you do 3 body interactions, you are done.
Okay.
Because the theory becomes stable with any number of orders you take. Yeah. Okay.
So you are saying that so far you have considered electrostatics. You are saying that there are other kinds of interactions, including solvent interactions and so on, but they can be electrostatic in nature.
That's what we are going to talk about. Yeah. Yeah, we will do electrostatics now. Next.
So this effective you have written, so 1 minus rho, that's a third virial coefficient term, that rho into P.
That rho is the third virial coefficient, essentially, yeah. Which is also related to van der Waals theory. You could do van der Waals theory, for example. Okay, so let us keep going.
So one more question about this. So in the we have find this n into power minimum as 3/5 for this excluded volume. So we in the globular phase we find is 1/3. So this is totally a volume argument, or is there a theory to?
Oh, it's yeah. Let's do that. I mean, okay. That's not my purpose, because I know you guys are doing simulations like coil globule. I know you are doing coil globule kind of thing. So let's do this, right? In view of the comments. So let me keep like this. I'm going to erase this. Okay. Now I put V3 3-body interactions, right? Here, 3-body interactions. What's the probability I'm going to get 3 monomers in the same place? That will be n over r cubed. That's the density. Power 3, and then total volume of the coil, that's r cubed. This is positive and this is negative. All right, that's it. I just said this. This is the n cubed by r to the 6. R cubed is here. So n cubed. I hope I'm not erasing too quickly. That's what it is. This is my 3-body interaction term. Let's do the calculation. dF by dr in units of kT, that goes like a r over n. There is a negative sign, and then there is a plus sign. So plus modulus of this n square over r to the 4, negative sign V3 n cubed by r to the 7, that's equal to 0. You can do it on a calculator if you wish, because it is not a very simple quadratic equation, but it turns out these two terms dominate over this, because when they are collapsing, intuitively you can think entropy is not going to be important. When you balance it out, you get r going like n power 1/3. Okay, and then V3 by modulus of V2 power again 1/3. So the r goes like n to the 1/3. That is a dull result, because now volume is proportional mass. R cubed goes like a mass. It's like a potato, collapsed object. Okay, so it's very simple, right? So you can really talk about the whole crossover instead of making this extreme limit. You work it out, plot it out. You'll see coil to globule transition nicely. You can also repeat this calculation, as I'm going to tell you in a minute, even when they are charged. Okay. 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 Good. Okay. So let me erase this. Yeah. Now what I like to do is I want, instead of this or in addition to this, I want to look at the charges. How do you do this? Let us go to basic electrostatics, right. Suppose I have a charge here, negative charge here, negative charge there, and the distance between them is r, right. I am not going to quiz you, right. The interaction energy, U electrostatic energy, as a function of r, distance between them, divided by kT, right, dimensionless, and that is equal to, let us say the charge of this one is the E square 4 pi epsilon naught permittivity in a vacuum, and the distance is r, and then there is kBt. Let me write kBt and then r. This is in vacuum. But in our cells, there is a dielectric constant epsilon, right. That is a dielectric constant. The dielectric constant typically is not a constant, as you folks know, right. It is a function, depends upon the scattering wave vector, depending upon the frequency, but in the static limit, in the so called hydrodynamic limit, it may approach like a constant. Yet it is a temperature dependent quantity. The reason why it is a temperature dependent is this captures solvent reorganization. When you change the temperature, dielectric constant changes because the water molecule is reorganizing. So that is captured, the solvation effect is captured by epsilon as a function of temperature, function of temperature. So when I go to the polymer here, right, and for other reasons, not every charge, suppose it is uniformly charged, every charge is not charged because the counter ions like to come and condense on them. I am not going to talk about it today. So, there is a, suppose I take one step length L, here I put one length L, there may be many monomers in here. So, the effective charge I am going to write it to be Zp, that is my effective charge for one charge. For another charge is Zp, so Zp square, right. And if it is a divalent, for example, you will put 2 square, things like that. But typically for every segment I am talking about, there is going to be some number of charges or essential valency, and then E is electronic charge, that is what that is. Typically what we write is, this we write it to be Zp square, what is called a Beerem length, Lb over R. Lb is called a Beerem length. It's an it's, we call it a length because it's a ratio, right. This is dimensionless. This combination should have the dimension length because R is a length here. This is therefore this combination is length. That length depends on temperature, epsilon, which also depends on temperature. Okay. But the meaning of this is this: if the distance between two ions is comparable to the Beerem length, this little r is comparable to Beerem length, then the electrostatic energy is thermal energy kT. That is the meaning of Beerem length. Beerem length is a length scale when the two charges are brought to that length scale, energy is thermal energy. If you bring it shorter, it will ripple like crazy. If they are similarly charged, if they are oppositely charged, they will just collapse. They make a co-acervation or whatever. Okay. So, therefore, there is an important length scale. Now, if you have salt ions on top of that, suppose I have salt ions here and there. Yeah, again your mean field theory can be worked out again by Debye and Huckel. Then what happens is this gets screened, this 1 over R interaction gets screened to give me 1 over e to the minus kappa R, where kappa is 1 over, this is called a Debye, C Debye length, and kappa is proportional to square root of salt concentration. Okay, that is how salt appears. Okay, salt concentration, how much monovalent salt you put in, right, potassium chloride, sodium chloride type, square root of that is kappa, that kappa appears in here. So, this looks like Zp square Lb over R e to the minus R over C, correlation length, or it is called screening length also. If you put a lot of salt, what happens? If you put a lot of salt, kappa goes up, that is the screening length is short, and kappa square root of salt concentration, if this goes up, this goes up. So, e to the minus kappa R, this is a large number, gets screened out. All the attractions and repulsions that you are going to see are going to be screened out if you add a lot of salt.
Now, say that I have some protein DNA interaction. So I have protein-protein interaction and also protein-DNA interaction. But the way so if I increase the salt concentration, will the effect be the same for both protein-protein and protein-DNA interactions?
Yes.
Or it will be the same.
It will be the same.
Universally,
It will be the same, except the ZPs. Which part of your sequence of your DNA, what the charge density is, which you are going to adjust with your pH. For the proteins, amphoteric, right? You could adjust the charge density with for protein DNA, not for DNA. DNA phosphoric acid is very strong, but you could compare. So therefore, that's how the recognition or interaction get modulated. So thank you for asking that. So the pH and Q appears through Zp, right? Salt concentration appears through the range. The strength of the interaction is adjusted by pH, and the range of the interaction, whether it's a long range or short range, is tuned by the salt. And when you talk about sodium pumps, we have salt concentration gradients, right? Not only that, when you have pH gradient, right, that's equivalent to having gradient salt concentration. Okay, so you know, right.
So, Muthu, I have a question. So, will Debye length have an explicit dependence on the concentration? Like, will it and very non-monotonically, right?
Yeah. The question is, let me say it in a different way. This is an approximate theory. It works like charm. The Debye-Huckel theory is an approximate theory, right? For all practical purposes of like 150 millimolar salt, it's okay, right? Up to that much. If you go to 1 molar, then it's not okay, because thanks to this person Abhiram, there are lots of clusters of ions, lots of correlations that happen. But we don't. Only in simulation you have to worry about it.
Yeah.
not in real biological systems.
What is Cs?
Sorry, salt concentration. Concentration of salt concentration. Molar. In molarity. Cs. How much salt you put, like sodium chloride or potassium chloride.
I have a doubt. So you are defining GPS for the whole chain, not the local.
Say that again.
You are defining
ZP.
as at the position R or for the whole chain.
No, that's what I told you, right? Only for the local. Every segment there is a length L. In the length, what the charge is, right? Not for the whole chain. Not only local, just per segment. Per monomer, if you like, per monomer. You can take ZP to be 1 if you want, if it's flexible enough. Okay?
Can we somehow plug this thing into our three-body interaction to get some type of correlation between Rg and concentration of salt?
We are going to do that, right? A two-body interaction, you mean?
Okay.
Right, two-body interaction, right? We are just building the Hamiltonian here, right? Okay, so
So increasing the concentration, salt concentration, is making the short interaction, the long range interaction to the short range interaction because of screening.
we are going to add it. No, I have not done anything yet, right?
No, if we take this thing, exponential minus r by kappa r, if we increase kappa because of this CS thing, that means we are making it short range. Like the interaction becomes short range. Do we have any threshold of that short concentration so that we can ignore the charges as well?
No, we cannot ignore it. Just wait. Yeah, that's what we are building up, right? We are going to do it. I'll answer your question, right? Okay, so I have to bring this into our Hamiltonian, right? So how do you do this? In addition to this, I have negative half ds 0 to n, ds prime 0 to n. And then I have this guy Zp square Lb over R s minus Rs minus Rs prime e to the minus kappa Rs minus Rs prime. Yeah, that's good enough. That's our Hamiltonian. Okay, our Hamiltonian will have chain connectivity, short range extra volume interaction, because the polymer has a backbone, it has various groups, we will have that part. On top of that, if they are ionized, if they are charge bearing, some monomers are charge bearing, then we put the sequence. Let us assume all of them are charged, and then we will have this one. Okay, that is our starting point. And I do not want to do the calculation.
Where is the sequence coming in here?
Say it again.
Where is the sequence coming in this?
I did not say it is a homopolymer, no sequence here. If you have sequence, you will have this sigma s prime. I did not do that yet. Okay, but you can do it. You put sigma s prime and do the double integral if you want to do it for your IDP. That is trivial. Right. Trivial means straightforward. Okay, so how do we do this? Before I would do the calculations, I want to think a little bit deeply about this. Right. Okay, so you guys, some of you were in the other class. Okay, so let me write V electrostatic, that is this part, right? Let me do a Fourier transform of this. That is equal to dr 3-dimensional dr, and then Vp square Lb over r e to the minus kappa r. Okay, you do it, 3-dimensional integral. Okay, e to the ik dot r. The way we talked about it. The answer turns out to be 4 pi Vp square Lb by k square plus kappa square. Okay, this is I told the other audience that this is a very important integral. We milk it in all physical disciplines. Okay, so
One question. So, I mean, you at some point you remarked that so if you add electrostatics, things become really complicated. Where does the complication arise?
there is no complication. Wait,
So it's not come yet.
not yet. Yeah, it's right, not yet, because the complication comes because we do not take enough time to think deeply. We just rush to the calculation. That's where the complication comes. Just think about it very quickly. The reason I am doing this for Fourier space is the following. Let us look at this one. Suppose k times the Debye length is small. Okay, Debye length is what, a reciprocal of kappa, right? Right, and that means what? Right, kappa is what? Kappa is large, right? Kappa is large. When kappa is large, CD is small, right? Okay, what happens? Look at this. What happens to when kappa is large? This is high salt. Okay, high salt means large amount of salt. That is, a kappa is large. Kappa are large, right? Salt concentration is very high. What happens? This is large. Therefore, this turns out to be 4 pi Zp square Lb over kappa square. Okay. There is a very important conclusion that comes out. Kappa square is salt concentration. I have not erased it, right? Kappa is square root of salt concentration. Kappa square is salt concentration. Okay. Let us look at the other limit, low salt. When low salt, this is zilch, right? This is not important. Okay, low salt. Now that means now I get 4 pi Zp square Lb over k square. Because this is not that important anymore. So these are the two limits. Okay. Right. Now let's look at the consequence of this. Right. Sandeep, now, right, you know that, right? You go here and you do the inverse Fourier transform, you will get the Coulomb. You will have, without this term, you will have 1 over r. Right. That means what? That means if you have no added salt,
Then it's just the
Coulomb interaction, the chain is going to swell, right? And this is, unless something else happens, this is like a nuclear bomb. You are putting a lot of charges, every 0.2 nanometers, 0.1 nanometer is going to explode. That cannot happen. That is where the complication comes. But what nature does is the counterons come in condense. The portion, because that is not allowed. You don't want to have bombs in your body. Right? This is called the charge renormalization, charge regularization. It automatically does. Okay. So let us not go away. So that is where the complication comes. But now let us look at the consequence of this. Suppose this is a constant for all part. There is no r here. If that is the case, right? This term comes like what? So what is the Fourier transform of this? V E L R is a constant. Fourier transform constant is what? Okay. So, the electrostatic interaction now becomes a delta function. Okay. Now, please go back and look at what we had before, the pseudo potential, right? We wrote this to be a delta function, I mean this, the extra volume interaction. So, now when I put salt, then it becomes exactly like this term. Life becomes very easy. Okay. In view of this, I think I am going to erase all these things now. In view of this, my Flory theory turns out to be Fr, well, not Flory theory, then the Edwards Hamiltonian becomes, right, e to the minus 3 over 2 L square 0 to n ds dr by ds square plus V plus 4 pi whatever this is 4 pi LB Zp square LB over kappa square, right, yeah, ds 0 to half 0 to n d exponent 0 to n a delta of r of s minus r of s. And we have already done all the work that we need to do. There is no new calculation to be done, really.
So now, so in your recent, one of the recent things that you did, you basically added a term for the dipole-dipole interaction to this kind
Yeah.
of moment.
Yeah. Similarly, so that's how you build the picture, yeah, and quadrupole, everything. Life is simple. We want to make life simple. Yeah. Okay, but there is a very profound result that is gotten by recognizing the simplicity and exactness, exact simplicity, right? Let us do this, right? I already told you this V is 1 minus 2 chi. L cubed, yeah. L cubed, yeah. Thank you. And here is the length. Kappa is 1 over length is the length cubed. Yeah. So okay. Okay. So okay. L cubed. Let me take. Yeah. You take that dimension. That's not important right now. Okay. We know the dimension is okay. Now instead of this, I have now plus 4 pi Zp square LB kappa cubed, sorry, kappa square. Let me make like this, L cubed. Okay, that's the length. Here is here, length cubed, that goes away, no dimension, and that's what I get now. Instead of 1 minus 2 chi, I get this. And that means I could define chi effective to be equal to chi minus 2 pi Zp square LB over kappa square. That's my chi effective. As when I put the salt, the chi that I had before, that chi, Z, this is the coordination number kbt epsilon 1 2 minus half epsilon 1 1 plus epsilon 2 2, or this little v, the radial distribution function that I wrote down, second variable coefficient wrote down, that now becomes like this. Remember, chi is like 1 over temperature, right? Chi is like 1 over temperature. So what I am doing is, by adding salt, I am dramatically changing the effective value of chi. That's how, you remember in the phase transition, liquid-liquid phase separation, I told you if chi is sufficiently positive, it will phase separate. So I can adjust the phase diagram with the salt, and Mother Nature does that. Now let us look at the consequence of this. Suppose salt concentration is low. I lower the salt concentration. Please take enough salt in your food. Suppose you take salt concentration low. What will happen? That means what? Kappa square is large.
But you define this for salt concentration high. This one.
Let us assume for all practical purposes, this is good for a salt concentration greater than 10 to the minus 3 molar. Okay, 10 to the minus 3 molar, that's small concentration, that's what we did. We established by experimentation 10 to the minus 3 molar salt concentration is belonging to the so-called high salt limit. Okay, what is high and low, right, is you need to establish. 10 to the minus 3 molar belongs to high salt limit. Okay, right. And yeah, if you drink a lot of water, there was a radio station, right, with a competition for people drinking who can drink lots of water. And one woman drank a lot of water, and in such a way salt concentration was so low she died. Okay, that's the extreme amount of water she took. But anyways, so there are good reasons why we don't have 1 molar KCl in our body, right? Anyways, so for all practical purposes, most of the biological experiments, we belong to high salt limit. Therefore, life becomes very easy for us to theorize. Anyway, so let's look at salt concentration low. When you lower the salt concentration, kappa square becomes smaller. When it becomes smaller, this whole thing becomes a larger. When the whole thing becomes a larger, what happens? There is a negative sign. Chi gets reduced. What happens when chi gets reduced? Homogeneous, immiscible. It makes sense, because when you have larger salt, charges get screened out, right? Not screened up. When the salt comes lower, the charges are manifest, they repulse, so they spread everywhere. That's why they become miscible.
So Muthu, just like to, as a corollary, so say that I have, it's against inside cells I have a multi-component system, right? So some droplets of different kinds. Now I want to dissolve some droplets in a selective manner, say. So then, perhaps based on the charge and interactions and so on, if I add salt, I can actually control that as well, right?
Absolutely, absolutely. See, this is, look, I mean, I'm a lucky guy, right, to recognize simplicity. The way I would do that is through ZP, right, LB, which is dielectric constant, which is temperature dependent, solvent reorganization, and then of course salt concentration. In the simplest way, you could tune it the way you want to do it. In we talked about membraneless organelles. There are no pumps, right? How do they go in and out, right? So these are the kind of things that a combination of these things, but it's okay. Anyway, so that's what happens. So therefore, for phase separation, the critical value of chi. Remember, we had a formula. Critical chi is equal to what did we say? Square root of n1 plus square root of n2 whole square root of 2 n1 n2. We had that formula. That formula gets modified with salt, and you can do it. There's a homework problem. You can do it before you do any simulation. This is the kind of thing that you should just dwell on it. Write it on a piece of paper. Think about it. Then go to computer simulation and do better. Okay. So this means lowering salt concentration is equivalent to what? Is equivalent to raising the temperature, right? Because it's spreading. At a high temperature, it's homogeneous phase. At a high temperature, it's homogeneous phase. That's equivalent to lowering the salt concentration. When you add salt, it's equivalent to reducing the temperature. So for biology, salt is much more powerful than temperature. In cosmology, there is no salt. You tell your friends. Okay, very profound, very simple. I mean, it comes elegantly here.
So Muthu, are you going to talk about the pH part?
I'm not sure. I don't think we have time.
Yeah,
Okay,
so
we don't have time. Not today. Not even Wednesday. No. Yeah, I want to talk about kinetics. Before that, I want to talk about structure in interpenetrating systems. So which I'll do. I don't know how much stamina you have. Do you have? You have 10 minutes, 15 minutes, you folks? Let me ask the younger folks. We are young, so we have a lot of energy. How about you guys? How about you?
yeah, I have all the time.
You have all the time. But the question is, do you have energy? Yes or no? Shall we? Okay, let's finish it. Then we can move. Is that okay, Sandeep? Professor Sandeep, is that okay?
Ask those guys to wait. Perfect. So you have some coffee or
Sorry, can you remind me what does homogeneous mean? This is I forgot.
Uniform. Every monomer is charged.
Every monomer is
Uniform charge. Same way. That's what a homogeneous means. Homo, not homogeneous, homo. And then hetero means you have different things. Protein is a heteropolymer because there are 20 amino acids, right? And the DNA is a heteropolymer, right? Because 4 nucleotides, they can come in different ways. Homo means every monomer are identical. You can have a homo RNA. Suppose you have uracil, that's a homo polymer or poly A. Right. Okay, so let's go on with the structural research. So I think I have said enough, right?
One question. Yeah, there you told that pH is related to this ZP. So if like how that connection can be made? Like
Yeah, I think that will take a long lecture. So you have to do what's called a titration curve. Yeah.
Which is the protonation states.
Yeah, titration curve. That's
Next year Muthu comes, he'll have to do it again. So we'll force him.
you are going to take over, right? Okay, so right, good. So now let me tell you. In the interest of time, I'm going to be quite simple. Quite simple. This is ds n ds from 0 to n minus r. Okay, so let's do this. This is the important theorem. All right. I hope you can understand this. This is the important theorem. Okay, and let's keep that. Let me write in one more formula here. This is equal to, in Fourier space, this is equal to Vk momentum space. That's equal to k square plus kappa square. Okay. The extrude volume case, when you do the Fourier transform, and that V of k is simply a number. Fourier transform delta function is 1, so that's simply V. Okay. Fourier transform of that interaction is simply V. Fourier transform of this interaction is 1 over k square plus kappa square. I'm just rewriting it. Now let me go to a collection of polymer chains, okay, and they are interpenetrating. And now the way I want to do is I want to do in a cartoonish way because it is too late and the calculations are too long. Let me imagine a situation where this interaction is V. This is a usual short range interaction V. Delta function interaction, but Fourier space is simply V. Now what I like to do is this interaction now gets, when the chains are interpenetrating, what I will have is I will have something like another chain comes in here. Let me draw a different chain like that. Okay. So now I have to worry about interaction between this and that, and between that and that. So I worry about this interaction. Now when the chains are coming into play, I have interpenetrating chain. Now I have this interaction and that interaction together, and then I have to build this picture on and on, right? And then 2 other chains come in. For example, I draw a cartoon like this, right? And then I have blue chain comes in here, and then another red chain comes in here, say for example, right? Then I have, oops, sorry, got this like that, and on and on. Okay.
So if I have many chains of the same kind, right? Can I think of a mean field approach where essentially like what you have?
This is they are identical chains. Okay. They are not a different chemistry. Identical chains. I'm just looking at a homopolymer again, but you can build this picture for heteropolymers also. Different kinds of polymers. I'm taking many chains of same kind. Okay. The way we do this is, please let's be graphical, right? The interaction here is V, right? Only short range interaction, no electrostatic fiat, right? And I'm trying to figure out what the effective interaction is, which I write it to be delta. and let me write in terms of Fourier space. Delta k is equal to, here it's V. What is the next term? I go to, it turns, when you expand this, there is a negative sign. Next term will go like, here is V, okay, V, and then here is a correlation between two monomers, all right, and the number of times, the chance that I am going to get the blue chain is some concentration C, and let me write this to be S of k, right, S of k, right. I take the long chain. Remember we talked about a Gaussian chain. When what is the correlation between two positions of the chain? I am working in momentum space, Fourier space, that is my S of k, and then the next term would be, here is V. Let us keep going. The next term will be plus V C S k. S k is 1 over k square. Remember the fractal dimension of a Gaussian chain is 1 over k square, right, in the high inside the polymer coil. And then I have V, and then again C S k. C is concentration of the polymer. C S k, and then another V plus etc.
So, is it like you have to develop that there as Feynman diagrams, like of different?
Yeah, I won't do that because that's what I should do, but that will take a long time. But please look at the structure of this. It's simply a geometric series. Okay, if it's a geometric series, then what I have is the effective interaction. You will see in a very few minutes, in a couple of minutes, you will see the elegance of this. The effective interaction of Fourier space is equal to V divided by 1 plus a C S k V. Okay, V is a common factor. 1 divided by 1 minus x is equal to 1 plus x, blah, blah, blah. 1 divided by 1 plus x, 1 minus x, etc. And S of k is k square, 1 over k square for Gaussian chains. Inside the chain is topologically correlated. We know that 1 over k square. If this is the case, what do you get? This will go like, right, V 1 over k square at the top, k square plus CV. Okay, k square in the denominator, k is 1 over length. We talked 1 over length square. So I could rewrite this to be V k square divided by k square plus c to the minus 2. You remember we talked about Coulomb's interaction, k square plus kappa square charges. Here are no charges. This is a complete neutral case. But that the structure, when you look at collective behavior of lots of chains, the effective interaction now turns out to be V k square divided by k square plus c to the minus 2. Okay. And what is c? This c is going like 1 over c square root of 1 over cv. Polymer concentration times v is your half minus chi or 1 minus 2 chi. Okay. This c is called Edwards length after the guy who did this. This is very, whenever you read the polymer literature, you will see this number. Okay. That means the external volume interaction that you had is screened. The meaning of that is, originally I had this interaction. Because of the interpenetration of the other chains, the net effect of that is to screen this. Therefore, when you go to higher and higher concentration, although it's a good solution, swollen chain, when you go to higher concentration, it becomes like a Gaussian chain because the external volume interactions get screened by topological. It's called a topological screening. I call it topological screening. Okay, that's for the neutral case. If I plot this delta k as a function of k, right, very small k, nothing happens. Here quadratic, it goes like this, it reaches something like this. There is no structural evolution. It's all uniform. Okay. Now let's look at the charge system.
So does it mean that if we have a high concentration, it will become an ideal kind of thing? I mean,
Yeah. Every chain, every label chain becomes a Gaussian chain like, and that's demonstrated experimentally. Okay. All right. So now let's look at the charged case. In the charged case, same formula, right? V, the same thing, it's going to look like this one, except now what is V? Vk goes like 1 over k square. Let me take the extreme limit, low salt. Vk goes like 1 over k square. We just did it somewhere. Vk goes like 1 over k square in the low salt case. If that's the case, let's look at the delta k. Delta k goes like Vk, V is 1 over k square, 1 over k square in the numerator, 1 plus C, S of k is 1 over k square, and then V is 1 over k square, so it is k to the 4. Okay, V is equal to 1 over k square, 1 plus C S k goes like 1 over k square, and then another V 1 over k square, that's what you get. So, this means k square, we're leaving out all the prefactors, so you can work it out, right? K to the 4 plus C. Oh, I forgot about the LB and everything, right? There is an LB here. Vk goes to LB over k square. Maybe I should write down LB over k C LB. This I could rewrite to be k square divided by k to the 4 plus some correlation length minus 4, dimensionless. And then C, therefore, this correlation length now C goes like concentration of the polymer per minus quarter. That's what you get. Okay. But let's plot this out. Delta of k as a function of k. Who wants to do this for me? K is small, right? This is not important compared to that. So it goes k square. It goes like this, right? K is very large. K to the 4 is more important than that. So 1 over k square. So it starts like k square and comes down as 1 over k square. So it will show a peak. That means there is some intermediate, you can work out what length scale that the peak is going to be. That means there is going to be structural evolution where finite size structure is selected. Be selected spontaneously. So when the electrostatics is important, then you will have what we call polyelectrolyte peak. We observe this experimentally, well established agreement, it agrees with theoretical calculations, right. So there will be a spontaneous selection of certain sizes, certain length scales, even in the daughter phase. When you have macro phase separation or so called liquid phase separation, if there are charges there, there is no chance of avoiding formation of internal structure of finite length scale.
And that is what like you think some of these internal structures.
And why does it trap in that finite length structure?
Because of what I just derived. Sorry?
Yeah, I mean the delta K.
Delta K, yeah. Because they are correlated. They are all the chains are interacting with each other, right, and they are contributing to the structural evolution. It's a combination of what is the blue term is a topological correlation, form factor, structure factor. And the V is the yellow term is electrostatics. So the collusion, right, between electrostatics and topological correlation. Electrostatics long range, topological correlation long range 1 over k square when you do the Fourier transform like 1 over r. That those two long range correlations are conspiring to give you the spontaneous electric structure.
Now if you take a heterogeneous charge distribution, which is I am guessing for proteins that would be the case, then will that lead to some interesting?
Yes, indeed. It will also be spontaneous. This is something that we have recently shown. That's why we are interested in this, right? Yeah. So you can repeat all these things, right, with these terms. That's Sandeep's question. You can repeat it, calculate it. Just to follow our earlier work or somebody else's work, just do it. So if you say uncharged, there is no spontaneous selection length scale. Then it's a usual oil in a water droplet. But as soon as you have these charges there, depending upon charge density, all those things, then these things go out. Okay? I think this is a good place to stop. I had one more thing to say, but it's too late. Yeah, questions please. Yeah, additional questions.
When we were introducing the electrostatics in our model, we introduced in two body system. Why not in three body? Why not in the third virial coefficient? Only in the second one.
There is no need. There is no need, right? Why okay, so what are the, when you put electrostatics, what are the possibilities? What are the two possibilities?
Attraction and repulsion.
When it's repelling,
Okay, so
there is no need. It's when we expanding, no need. If it's collapsing, you have three body interaction anyway from preventing it to collapse into a black hole. So there is no need for that. That's the reason. Yeah. That doesn't mean there are no multi-body electrostatic correlations. There are multi-body electrostatic correlations, but that's at a higher order level. Yeah. But not for the purpose of you were asking why. Yeah, why do we? Yeah, you don't need it for the purpose of preventing collapse because we already have it. Okay. Okay.
Can you repeat what is happening with the phenomenon of spontaneous selection of lens?
What is this?
The spontaneous selection of some lens. What is happening there? Can you repeat it?
Okay. When you calculate effective interaction, right? Effective interaction as a function of k, you get a peak. That means what? That means there is a certain reciprocal of k is some length. There is some finite length, some non-zero finite length, which is preferred for them to organize.
And what is physically happening in the solution there?
That is the theorem length or no?
This that's right. That length you minimize this. Come on, you can take this, you can minimize this, right? When you minimize this peak position would be at 1 over c. And 1 over c depends upon this guy. Okay, C LB like that. C is the protein concentration, LB is the Beerem length, right? Beerem and the ZP square, all those things go in here, and that's how you tune it. Okay. So some length is preferred, spontaneously preferred, because that's the free energy minimum. If that's the case, that corresponds to free energy minimum. If you go through our papers, you will see expression of free energy, the scattering function is the function of delta k, but the punchline is simply this. You can tell, but for a particular value of k, the effective interaction is a maximum. That means that for the reciprocal of that k, that length, the free energy is minimum, or radial distribution function is minimum.
Yeah, that is what I was asking.